So I'm going to really, I used to call this talk designing MPI applications, but that's a bit like having a talk called writing C programs. You know, I've been learning C or Python or Fortran for the past few days. It's quite a kind of a meaningless statement. So I think what's more useful is sort of tips and tricks. It's often useful to point out common errors or understandable but common issues that people come across that I've seen over the years, and we can discuss these. So please chip in. You may not agree with some of these statements. Please chip in with any questions you have. But I'm going to go through these topics. This is the list of, so the aim, of course, for us is to write correct MPI programs that are portable to many systems. Okay, and that's the big issue now, because people often develop purely on their laptops and don't think about portability. That are efficient and easy to maintain. Okay, so that's an important thing we need to do. I'm going to cover common issues here. So here's a kind of a list of the issues that I'm going to cover. I've been refactoring this. I can't guarantee I'm going to cover them in this order, I'm afraid, because I've pulled together a bunch of different talks. But I hope I will cover all these things in this talk. Issues with MPI send, which is kind of done to death. Data sizes to do with portability. General non-portability issues. People writing programs with specific process counts, not calling collectors collectively or correctly. Incorrect use of non-blocking, which is very common. Lots of small messages. Array allocation issues in C, related but different array syntax issues in Fortran. General issues to do with code design and readability and debugging. So I'm going to go through these relatively quickly because I think it's quite a long talk because of it. I've brought together a number of smaller talks together. I think they do fit together well, but there's maybe a bit much here. But I'll go through it. Please, if you want more detail on anything, just send it a chat message. But I'll go through them relatively quickly, but hopefully explain all the issues. So I've talked about this all the time before. Really common problem is people assume MPI send is asynchronous. This leads to potential deadlock. You may be assuming MPI send is asynchronous. It often is buffered for small messages, but the threshold will vary with implementation. And what happens is your code may run on one machine and deadlock on another, because on one machine you may be relying on the fact that MPI send returns control to you before the receiver is issued, but if it doesn't, then it will deadlock. So you can check if your code is correct always by a correct code should run with all MPI send calls replaced by MPI send. That's a good check to do, okay? So if you have a code that runs on your laptop and doesn't run on Archer or Archer 2, okay, rather than spending ages trying to debug on Archer 2, take the code on your laptop where it works, replace all the sends with send and run it. And if it doesn't run, then you have a problem, okay? And you should fix it on your laptop first. The reason why this is an issue is that as you go to more and more processes, the system can reserve less memory for these buffering. So typically the threshold when MPI descends to switch between asynchronous and synchronous send will get smaller on very large machines because you just don't have enough memory with all these processes. So that's why you often get this effect that it runs on your laptop where the threshold is very large and maybe not on a large machine where it's smaller. Okay. I wouldn't recommend the use of bsend, but remember you can't assume there will be space for MPI bsend. In fact, the default buffer space I think is 0, so you need to use MPI buffer attach. That is capitalization was wrong there. It should be lowercase a. I will just fix that while I'm here. In fact, I think I mentioned during the lectures that if you're going to be buffering 1 megabyte messages, you need more than a megabyte of storage. And if you look at the MPI standard, there is some guidance there on how to estimate how much. And there's a magic constant called MPI bsend overhead, which is the size. It's all rather horrible. That's why I don't. But this is the real biggest issue. The biggest issue we have when people come and say, Archer is broken, my program doesn't work, but it runs on my laptop. The normal reason is they've made incorrect assumptions about MPI send. And it's unfortunate in MPI that it's so complicated, but we just have to live with it. Data sizes, be careful of data sizes or layouts. If you're a Fortran programmer, you should, and you're using the sophisticated type system, you'll say you'll be asking Fortran to give me a variable which is big enough to hold a double precision, hold a floating point number of this precision and accuracy or whatever, You should inquire at runtime how big. That's true for C as well. You should not assume an integer is 4 bytes or a float is 4 bytes. You should inquire at runtime. So in Fortran, the issue comes about, and in my Fortran 2008 example for the Pi, I showed you how to do that. I didn't cover it in the lectures, but it's in that example. And in C, compiler-dependent padding for structures, you have to. So you really have to inquire these things at runtime. Don't use magic compiler flags to change precision, though. You'll see people who have a program they wrote it using floats and they really want doubles. They do CC minus convert floats to doubles. Don't do that, because of course when you change precision, you don't only have to change the floats to doubles. Everywhere you say MPI float, you have to say MPI double as well. So when changing from say float to double, you must change all the MPI types. So actually, if you're going to be a purist, a really nice thing to do is to actually to parameterize this in C, and I'll cover the Fortran version later, into a precision file, precision.h. So what you have is you have a precision.h file which you include in every function, and you do something like type def float real number, hash define MPI real number MPI float. So in your code, you never ever say float or MPI float. You say real number X and MPI routine MPI real number, and that allows you to switch. If you just change these two lines in this one file and recompile, then you change float to double and MPI, your code recompiles. Why is that useful? You might say that's pointless because I'm always going to use doubles. I've never got floats. Well, actually, being able to reduce the precision is a useful debugging aid, because often you'll see an error. You'll run the program, you make some update to your program, and you're in double precision, and the answer changes by some small amount, 1 part in a million, and you're thinking, is that a bug or is that a rounding error? It's very hard to tell them apart. However, if you can reduce the precision, and the error goes up, then you've got good evidence that it's a rounding error. If you reduce the precision and it's still wrong by 1 part in 10 to the 6, it's not a rounding error, you've got a bug. So you might say, why would you ever want to reduce the precision? It's actually a useful debugging aid, I think. But the problem is you have to double specify, you have to define the variable and pass it to MPI. So if you're using magic compiler flags to change the precision of variables, you should just fix your code. In Fortran, it's just the same, but you have a module with parameterized types. You have parameter real number equals kind of 1.0 E0, MPI real number is MPI real, and then to change it, you just do kind equals real number, and then to change it, you just go MPI real to MPI double precision. So it's the same thing. So this is a useful technique to do. Non-portability is probably the biggest issue. So, a correct C code should compile correctly with any C compiler. A correct Fortran code should compile correctly with any Fortran compiler. I really don't like it when people say my program requires GCC 9.8.5.3.2, and you're like, why? Okay, unless there's a bug in the compiler, typical reason why people say my code requires. There are two reasons why people say my code requires this compiler. The normal one is their code has got a bug, and they're just lucky with a particular version of a particular compiler, the bug doesn't show up. The other one you hear people say is, oh, well, in this particular compiler, there's this really clever extension. Well, don't use clever extensions. Code should be portable. You should write simple, portable, easy to maintain code. How do you check that your C code is portable? You should run using multiple compilers. When you're developing, don't develop for 2 years using GCC and then go and try it on the Intel compiler. If there's a bug, you've got 2 years of code to debug. You have to continuously, as a development process, compile using multiple compilers, C and Fortran. The same is true for MPI. Run on more than one machine. Now, actually, you really want to use different MPI libraries here. So the correct MPI code should also run correctly with any MPI library. So the problem is many parallel clusters will use the same open source MPI. So you might have 2 machines which look completely different, might have different processors. One might be AMD processors, one might be Intel processors, one might be ARM processors. But if they're both using, if they're all using OpenMPI or all using MPI CH2 as a release, that's not going to stress it. So actually, the nicest thing to do is to run on more than one implementation on the same machine. So ideally, on your laptop, you have multiple compilers and multiple versions of MPI. say MPI-CH2 and opening MPI on your laptop. So it's a very useful test. On a cluster, Archer, very high-end machines like Archer and Archer 2 are unusual that there is one true MPI, one MPI to rule them all, which will be the Cray MPI. Most clusters, like our mid-range Cirrus cluster, which I'd hope to use for this course, will have more than one MPI version, maybe MPI-CH2 compiled with the GNU compiler and MPI-CH2, that's just switching compiler, so this is not a good example. But often a cluster machine, a mid-range machine, will have multiple MPI libraries. You might have the Intel MPI library and OpenMPI, and running on those two is really, really useful. So you should get into the habit of switching, regularly testing your code against different compilers and different libraries. And that means if you have a bug, it will show up early, which is what you want. Code readability. Adding MPI can destroy a code. You haven't really seen that yet. But basically, if you compare the serial and the parallel versions of the case study, which is a very simple example, the parallel code is full of all kinds of junk, MPI junk. We'd like to maintain a serial version. Why? Well, really for debugging, it'd be really nice to be able to run a serial. By serial code, I don't mean the parallel code on one processor. I mean run the parallel code when there isn't an MPI library. And why that is useful is a good debugging aid. You're working on your code and you suddenly notice that the answer is wrong. Is it a problem with your MPI, or have you just got a good old-fashioned bug where you've got some bug in the computation part of your program, not the communication part? Well, how can you tell if you don't have a serial program because you've killed it with all this horrible MPI? So the approach you should do, and it's a really good general approach, is to separate off the communications routines. Don't stick in MPI send, MPI or reduce everywhere you need it. Say to yourself, and it's a very good way, it's a very good mental discipline for when you design your code, what parallel operations am I going to need in this program? I'm going to need halo swaps. I'm going to need global reductions. So write a halo swap routine and write a global reduction routine and implement then an MPI, but it makes the code much easier to read and also much easier to maintain a serial version, because you can maintain a serial halo swap or a very simple piece of code which does that. So this is a technique. People used to do this all the time in the past when you couldn't guarantee what the message passing library would be. You define your own set of communications primitives and then implement using MPI or PVM or whatever the message passing library was. Now, just because MPI is now universally available doesn't mean that it doesn't obviate that. That's still a good thing to do. So a really good, well-written code will have no explicit reference to MPI in the main code. It will call your own routines like global sum, halo swap, which are later on implemented in MPI. So, for example, it's a Fortran code here. If to initialize for MPI, you've got MPI error, MPI com size, MPI com well, all this stuff is horrible and looks disgusting. What you really want to do is you want to begin the parallelism and you want to know what your ID is, how big you are. So I wrote a routine called par begin, which does all the MPI stuff and returns the size and the proc ID. And actually in this program, because it was a Fortran program, I wanted to internally number my processes from 1, not 0. So I actually added 1. So in the main body of the code, I've referred to the processes 1, 2, 3, 4, 5. But when I send and receive messages, I do the remapping. So that means your main code has call par begin size proc ID, which is a relatively elegant call and would make some sense to a non-MPI program. Whereas this stuff, call MPI com size, it looks like gibberish. Of course, for a serial machine, you just provide alternative interface, which does nothing. Yeah. So it's trivial to implement this. The equivalent one, a good example is global sum. Okay, the thing you want to do most often in a scientific and technical program is take a partial value and accumulate it into a global value. So the call is call MPI or reduce dval, which is the value, dtemp, which is the answer. It's 1 MPI double precision, MPI sum, I error, and then dval equals dtemp because these have to be different. That's just a horrible 1, 2, 3, 4, 5, 6, 7. Wrap it up in I know in my program I'm only ever going to want to do a global sum of doubles. So I have a subroutine par d sum, which does a global summation of a double precision value. It takes one argument. So in my main code, I have call par d sum d value, which looks lovely and elegant, rather than all this rubbish here. And then again, for the serial machine, it's a null routine because you don't need to do anything. Okay. Don't do what I've seen some people do and write dummy versions of the MPI library calls. That's madness. You should funnel all your, and it will be accountably, it will be a 10 or so routines. You should funnel all your communication routines through 10 or so of your own interfaces and implement then an MPI. And then you have an elegant code, easy to read, and also easy to maintain a serial version because you have to only re-implement a finite number of functions. And then this comes from a code I wrote many years ago, but basically I had my sequential source. What that means is in these 1, 2, 3, 4, half a dozen or more routines, there is no explicit reference to MPI, okay? For some reason I had two library routines, dem parallel and dem comms. I can't remember why. But basically, if I want to switch, so my fake source was in dem fake par and dem fake comms. These are the dummy implementations of the routines. And the MPI source were these files. And basically, in my Makefile, if I wanted to compile the serial version, I said parallel source is MPI source. If I want to compile the serial version, I say parallel source is fake source. So I just recompile. I don't even need to recompile these functions. I just need to recompile and relink these. So this allows you to maintain and switch between serial and parallel versions very, very easily. So the advantage of this communications library, you can compile the serial program from the same source, which is useful. It makes the parallel code more readable, which is also very, very useful. And also, it's actually a useful mental discipline. It tends to, rather than sprinkling random MPI calls willy-nilly over your code, you step back and say to yourself, what are my communication routines as you have previously decided what your calculation routines are, and you implement them. It's not such a big deal now because MPI libraries are so universal and so well implemented. But until a few years ago, you might have gone onto a Cray routine and said, actually, we've got this parallel routine which does double precision global sums really quickly, quicker than MPI. Okay, so you'd like to replace all your MPI all reduces with this magic Cray specific library call. Well, that's going to be horrible. You might have 100 all reduces in your code. You're going to have to change them all. Not if you funnel them all through one routine. Apologies. I'm hitting the wrong key. Apologies. Sorry. If you funnel them all through this routine, I just need to change this one line from call MPI or reduce to call magic very fast Cray Shemem function, and my whole program suddenly does it. Okay, so it allows you to optimize for different libraries. Or different MPI. You might have a halo swap routine, and you might say, is it best to do with S send, send, B send, I send, I receive? Just re-implement that single halo swap routine in a number of different ways, and pick the most efficient one by, I don't know, measurement or something. But you should try and minimize your use of MPI or in fact eliminate your use of MPI in your main code, and have it all separated off into a bunch of library routines, which you have designed. A few round not calling collectives correctly. Collectives must be called by all the processes in the communicator. This following code will not work correctly in more than a single process. It's meant to be on. You can tell that I've recently refactored this call. So this, if you called an all reduce like this, an all reduce call like this would deadlock. Okay. This will not work correctly, okay, because this number cannot be broadcast to the other processes, because in the MPI in the message passing model, you have complete control over your memory. So unless you call a message passing routine like broadcast, your data can't be changed. So unless you are calling the broadcast, then unless every process calls the broadcast, this will not do what you expect. However, there's a slight technical point, but this function isn't guaranteed to deadlock. The all reduce is guaranteed to deadlock, but this one, the broadcast in this way of reading, might actually run, might not deadlock. It won't do it. Why did anyone think why that is? It's a slightly subtle point, but So you could implement broadcast by doing a bunch of, if you had to write the broadcast routine, you might implement it by the root at rank 0, doing a bunch of non-blocking, sorry, asynchronous sends, lots of B sends, and the other guy's doing a receive. If you implemented like that, if it was only called on one process, it would actually do all the asynchronous sends, return and carry on, okay? But the message would never arrive because it wouldn't be. Now, normally, if you don't call a collective correctly, it will deadlock. But there were a few where, well, but even in that case, it would not do what you would expect because the other process would not get correct values of X. The other thing I would recommend is really compute everything everywhere. Use routines such as all reduce in preference to reduce. If you use reduce, the value is only computed in one place, and that can be confusing because you will have a variable called pi on your program, but because you computed it using reduce, its value is only valid on one of the processes. That can cause bugs later on. So typically, and we could discuss this afterwards, but typically I would advocate using global reduction operations or reduce in preference to reduce. Normally there'll be no serious performance implications. I mean, I would generally recommend using all reduce, not reduce. There are a few cases where you can argue for using reduce, where it really isn't required. Sending lots of small messages, you often see this. We might be sending off our halo value, and people do for I equals not I less than I double plus, MPI send address of x1i, you're sending the second index. That, as we talked about, we had a question, every single send there incurs a latency of, say, of order a microsecond. A microsecond might not sound like much, but it's a lot. Modern processors clock at multiple gigahertz. They're computing at nanoseconds. So a single send operation is equivalent to thousands of computations. So message passing is very expensive. So you should not send lots of small messages. This, you can send a single message of size n. That'd be the right thing to do. Now you might say, well, I can't do that if I'm sending in the second index for a loop over j. Actually, I have this again. Apologies for these mistakes. I do apologize. That code has been slightly. It's confusing. I've copied another piece of code and used so I do apologize for these. Yeah, what I meant there is if you were looping over the first index, which is conventionally be called I, it would be strided. So you might say, I can't send anything like, well, use a derived data type, okay? So the important point is with a derived data type, you send one message, okay? It might not be as quick as the contiguous send because there's going to have to be some copying, but it will be a lot faster than sending. As I say, my analogy here is if I want to buy 10 pints of milk from the supermarket, I don't drive to the supermarket, buy a pint of milk and drive home, then drive to the supermarket, buy the second pint of milk and drive home. You drive to the supermarket, which is the latency, you buy 10 pints of milk and then you go home. That's and people, it's not that subroutine calls are expensive, which they sort of are. It's really that the message passing has a latency, which is 3 orders of magnitude more than a subroutine call because it's in the microseconds, not the nanoseconds. Some people program specific for process counts. When people do their pi example, they often write stuff like this: if rank equals 0, if rank equals 1, I less equal n over 4 I double plus pi is pi plus this. Else if rank equals 1, I mean, that's not. There are two things wrong with this code. First of all, it will only run on 4 processes, which is horrible. But also, you've got replicated code. This code here is the same as this code here. Replicated code, you should get in the habit of SPMD, single program multiple data. Have the same code, but mess around with the loop limits here. Have this as I start and I stop, okay? So, you should not write code like this. It's very rare you need code. You should try and write code which runs for any number of processes. However, that doesn't mean that the number of processes can't be a compile time constant. So a code, you might have restrictions. Your code might only run on power of 2 processes. Your code might only run on even numbers of processes. That's fine as long as you check at runtime. You know, if p is not an even number, print. If size is not even, print I can't run on an odd number of processes. But it's often easy to make p a compile time constant. That might not seem elegant. You might say, I want to have a program, a single executable that runs on any number of processes. But that can be difficult because in a real program, as you alter the number of processes, the data sizes get smaller. For example, if you think of the case study, by definition, the more processes you run on, your array size gets smaller. Your array sizes depend on your process count. And in C, particularly where dynamic array allocation is a bit of a headache, it can be nice to have p a compile time constant. There's nothing wrong with that as long as you put it in an include file or a module. You know, it's a compile time constant, and you check at runtime that size equals p. Okay, you have to do that. But a clever Makefile can reduce the need for recompilation. You know, often p may only need to be a constant in the routines that define arrays rather than use them. So, you know, I have seen people jump through hoops to have p a runtime variable, i.e. at runtime you inquire what p is from size. There's nothing wrong with having p a compile time constant. It can make compiling code now is relatively quick, and it can make things easy, but you have to check at runtime that people have compiled for the number of processes they're running on. Incorrect use of non-blocking. Okay, for I equals 0, for I equals 1, I less than size, I double applies. Well, send x to I, else let's do an I receive from 0. That's kind of an equivalent of the code that a non-blocking version of the well, this is sending data out, but a bit like a non-blocking version of the loop you had in your Pi example. That is wrong. Why is that code wrong? For 2 reasons. And now imagine we just start some computation. Okay, there are two reasons why this code is wrong. Can anyone give me an answer? There's no weight, absolutely. Okay, so there should be a weight. So that's the fundamental thing. But even with it, if I put a weight in, the code is still wrong. So that's the fundamental thing. That's the most important thing. But it's still wrong even if I put the weight in. Think about how many weights the rank 0 has to do. How many messages is rank 0 sending? It's in order, yes, but it's you have to have a request for every outstanding operation. How many outstanding operations does rank 0 have, and how many requests does it have? So the problem is, I only have 1 request exactly. So the problem is that I send the message to destination 1, yeah. I send the destination I send the message to destination 1. I get my request back. I send a message to destination 2. I've overwritten the request. So I actually can't wait on. You know, even if I put a wait in, there are still some, because I've been stupid and forgotten these requests. So there are 2 things wrong with this. A, we need multiple requests on rank 0. So we have to have an array of requests, and they must be waited on at some later point, and the same for the. Now my point is, why use non-blocking here at all? A lot of people get obsessed with using non-blocking. Avoid this complication unless this is performance critical. I would say use blocking communication. Yes, it might mean that rank 0 spends a bit more time sending the messages out. It might mean that the receivers spend a bit more time waiting around. But if it's just a setup phase, which takes a few seconds, then your code is going to run for an hour. Only use non-blocking communications when they're needed, because this is a recipe for disaster to use them incorrectly. So not waiting on requests is by far the most common problem. But the second one is sending a message up, down, left, right, where you need 4 requests and only having 1. So you need to have multiple requests if you have multiple non-blocking operations outstanding at once, but you must wait on them. So if you want rank 0 to do a wait all, and the other ranks to do an MPI wait. But as I said, in this particular situation, there's no real reason to have non-blocking. So people tend to overuse non-blocking actually. Debugging. Debugging is hard. Parallel debugging is even harder. The biggest mistake that people make is they assume it's a parallel bug. You know, I've seen people spend days saying, you know, I've got this program and it goes wrong on 128 processes, and I can't find the bug. I've tried and I've tried and I've tried. Debugging a program on 128 processes is a nightmare. And then you say, well, run it on one process. Oh, I've still got the bug. Well, it's just a bug. So the biggest mistake people make is that they assume any bug is a parallel bug. So as soon as you see a bug, don't try and debug your program on 256 processes. Run the serial code first. Then run the parallel code with p equals 1. That's always a good test because, you know, you might have done some mistake which is actually shows up even, you know, you might, for example, have mixed up your tag and your destination or something like that. That might show up on one process, okay? Then run on a small number of processes. It's rare that a bug only shows up on a huge number of processes. And of course, debugging on a huge number of processes is difficult. Debugging a small number is easy because you can do it on your laptop. We saw that output can get interleaved. Sometimes writing output to separate log files can be useful. So rather than just printing to the screen, have process 0 write to log 00, process 0 to log 01. That can be useful. You need some way to switch this on and off, but in C it's easy. Instead of using printf, use fprintf to a file pointer, and you attach the file pointer to standard out. In Fortran, you can do the same thing. Instead of writing to star comma star, you write to a unit number, the standard output unit, which is conventionally 6. But you can attach that to standard out. So you can do the same thing, but that can be useful. Parallel debuggers exist. Well, what would happen here is, so for example, if you were doing, let's think about the traffic model with p equals 1, okay? You would issue a non-blocking send to yourself, which is fine, and then issue a blocking receive, which is fine. So actually, a correctly written code should run on p equals 1, and so what will happen is it will work. Yeah. So if you've written it correctly and you've avoided deadlock, sending a message to yourself is fine. It will just be squirreled away. It will be very quick, but it will execute the send. It will execute the send. So again, debugging on small numbers of processes is useful. A linear DDT is a very, well, actually I should call it ARM Forge now. They've been brought, but there was a British company called a very unusual story. A successful British software company, that's not unusual, but they made money selling software in parallel computing. That's very unusual because, of course, high performance computing is used, not entirely, but is a very heavy use in academia where we don't have a lot of money and we don't tend to like paying money for software. So distributed debugging tool by Linear is actually very, very good, but it's becoming the thing which is norm. There used to be one called Total View, but it doesn't seem to be so popular now. But it's a commercial product. So, you know, if you have access to a machine, and also debuggers are very complicated pieces of software. Learning a debugger is a very, they're very useful things, but they're not a panacea. So, you know, the general reason by debugging is people write their programs to be deliberately difficult to debug. So my favorite one's a silent program, okay? Someone says my program doesn't work. They do MPI run. That should be MPI run. I don't know, Dale. Linear was available on Archer, and we would like it to be available on Archer too, but it costs money, and I don't believe it is being provided. Now, there will be, Cray have their own, this is an old syntax. Cray have their own debugging tools, which we will be running courses on when Archer 2 comes up. Oh, sorry, I've managed to mess that up. We would like a linear DDT to be available, but I can't guarantee it as yet. So, so where did this crash? You know, if it run for us, you know, people do. You should there seems to be a modern, I don't know if it's a modern, but there seems to be a common style of program where people don't write things to the screen. Writing stuff to the screen can save you out. So did it run for a second or an hour? You know, if there was at least one print statement saying, hi, I've just started, right, it ran for more than a second, okay? Then I know that it's not an initialization problem. You might say it's obvious. Well, it isn't. In a batch system, you submit a job, you just get it. It may not be obvious if that ran for a second or for an hour. If it ran for an hour, you know the issue was probably at the end of the program when it wrote the data out. If it only ran for a second, there must be some initialization problem. I don't understand this style. Did it even start at all? It might never have even started. You might have allocated too much memory and it crashed before it even started. I don't understand why people don't write to the screen. It astonishes me, but people don't do it. They have the silent program. It is impossible to debug a silent program. Just print stuff to the screen. Then what people, so a program should output like this, yeah? Print how many processors you're running on, okay? When you do file IO, you know, say, just have, and then if you want to print data out, you have to get into the habit of printing the rank. X equals 3, X equals 5 is meaningless. You need to know. So you know, print, if you are going to write out critical data, print it out on rank. And then if you have an iterative loop, every 100 or so iterations, just say, here I am, okay? Because if it says started of iterative loop and never even prints and says prints iteration 1 and never prints iteration 2, you know that it's deadlocking on iteration 1, okay? But if you don't have any output, how do you know how far it got through? And just a few print statements. People laugh at there's a, you know, debugging by printf. Well, actually, it can catch 95%, if it's your own code, debugging by printf is a good thing to do, because I think, you know, just sensible output every now and again. Well, oh, look, it finished, but it didn't write the output. It must have crashed at the output. It didn't even start the iterative loop. It must have started the input. It got halfway through the iterative loop and crashed. That's weird. Maybe there was a numerical overflow. It gives you feelings for where did it crash? Where did it go wrong? Okay. So you tell people to write things out, and then they write this. They write raw numbers to the screen. Why, oh, why do people write raw numbers? You have to annotate, yeah? 135.6. It was rank 1, J was 3, and X was 5.6. Okay, I actually timed myself. It takes an extra, I said here, this is an overkill. Okay, an extra 5 seconds to type. You've got no excuse in Fortran, because in Fortran you can actually cut and paste the variables rank J6 and put them in your print statement and see it's a bit more of a hassle. It will save you hours of debugging time. Okay. Because you have rank JX. If you know that this is a J value and it comes out as -2, you think, wait a second, J can't be negative. But if you just write these out, random numbers printed to the screen are useless as debugging tools. They have to be annotated. So I'm telling you things here which help you to debug programs. They're not specific to MPI. It's just that debugging parallel programs is so much harder. You have to have very robust debugging strategies. And so, you know, print stuff to the screen, print meaningful messages at meaningful points, and put them in while you're developing the code. Put them in when the code works, because they'll save you when the code doesn't work. Okay. So a common mistake people make is they've got a bug in their program. Okay. Oh dear, my program doesn't work. Then they change something, and it works. But the thing you changed didn't seem to have anything to do with your bug. You had a bug, and then you changed a print statement or an IO routine, and it worked. Oh, that's great. Or everything's fine. No, it isn't fine. There's a bug. Okay, you've just avoided it. Okay, you've just. Or people say, oh well, I had a bug with the Intel compiler, but it was okay with the C compiler. I'll use the C compiler. No, you've got a bug in your program, and it's going to come back, and it's going to bite you hard. Okay. So it's really important to run your program against multiple compilers and libraries frequently, which means that you debug. You know that the bug has appeared in the past day, and that is debug. That is a tractable problem to solve if you've used revision control. But if you only know the bug appeared in the past year, and if you have a bug that disappears because you changed something that you don't think is relevant, don't ignore it. Yeah, it's lurking there. You need to go and find it. So when you debug, start with the serial code, then p = 1, then a small process. As I said, don't assume it's a parallel bug. There is an issue about verification. Is my code working? Should the output be identical for any number of processes? Well, this is very hard to guarantee, and so you have to accept in any scientific and technical discipline, any discipline where we deal with the real world, unless you're a mathematician you're dealing with integers. If you're an engineer, a scientist, a data scientist, a biologist dealing with real numbers, you are not going to get the same answer. So you have to have some definition of acceptable. We need some way of quantifying differences from the serial code. And remember that the serial code doesn't produce the right answer; it produces an answer, which is at the behest of rounding errors. So that is difficult. However, if I run the same executable on the same number of processes, should I have identical output for 2 runs on the same number of processes? Yes. Now, it's very easy to write codes that don't do that. We saw it in the simple pi example. If I accumulated the values by using an MPI wildcard, if I accumulated with MPI any source, I could run the same executable on the same number of processes on the same machine 2 times in a row and get a different answer. That program is impossible to debug. So all your programs should be written so that if run twice on the same number of processes on the same input on the same computer, they give the same answer. However, when you change the number of processes, you have to accept that the answer will in general change. It is possible to write programs that give exactly the same. Now, the case study is a very simple algorithm. It happens to give the same number of processes. Sorry, it happens to give an identical answer, regardless of the number of processes you run on. But that's very unusual. If you want to guarantee that for a general program, it is incredibly difficult to do and introduces huge overheads, and I would not recommend it. But the latter thing, the same executable run on the same number of processes on the same machine, I believe should give the same answer, and it's not hard to achieve that. You just have to avoid a few mistakes, like do things in the same order, i.e. don't use wildcarding. Optimization, this is a big topic, but basically keep running your code. If you run your code, then you work on it for a year, then you run it again and it's not very efficient, you don't know where it was. So keep running your code on a number of input data sets with a range of MPI processes. So normally rounding errors will just give you slightly different answers, and actually having a version, it depends. Why did you? So if you have a very numerically unstable code, then that can be an issue actually, and so it's okay. It might make your program run less efficiently because forcing the order of computation might be. So what was the problem? You had a problem with the order of computation. What was the symptom of the problem? Did it make your program crash or just give a slightly different answer? Why were you worried about getting a slightly different answer? That's my question. Yep. Yeah, but it changes the outputs, but slightly different. Yes, but and model. So I mean, it changes the outputs, but as I say, if we have a chaotic system as the TV version of it, a butterfly flaps its wings and you get a storm. Yes, you can speak. Yes, absolutely. It might be easier to do it if you speak. That's probably the best. You should have audio available.
Hello, can you hear me?
Hi, yeah, hi. Yeah.
Okay. So my problem was it's a biological simulation with organism that's evolving, and they have the phase of selection where you have to select the most fittest organism in a space, and the problem is that the fitness of the organism are computed with a set of doubles.
Yeah.
So these doubles are computed sum with each other, and it gives the fitness. And the problem is that some organism may have the same set of doubles, but not in the same order.
Ah, okay.
And thus, you can
So that's
have
an
difference
unusual.
in fitness, but but the organisms are the same.
Okay,
So
so that's an interesting problem. Okay, that's one I've not come across. Right, so you're saying that they are actually okay. So normally I would say, if two organisms have the same fitness to within a rounding error, the fact that in one run organism A is deemed to be fitter than organism B, and the other one, basically you have a chaotic system in some sense. But okay, so that's yes, that is a very interesting problem. So yes, there. I guess what you have to do is you have to order them. You have to order the inputs by sort them into ascending order or something. I guess is that
yes,
how you do it?
that's we did. We order all the doubles, and
Right.
so. But the
Okay.
problem is
So
the
if
efficiency.
you need to
You
know
said
that two
this.
things are actually equivalent, no, that's an interesting. No, so there, it's yes, that's a good solution. So I appreciate, yeah. Um, but yes, so there are cases where, but if you require that, you need to think very carefully, do I really require it? But it sounds like your case, yes, it sounds like you require it. So yeah, it sounds like you have an interesting, a non-typical but interesting case where you need to do that. Yeah, that's an interesting point. Yeah, that's a nice example, actually. Yeah, okay. Is that okay? That's a very interesting topic. Okay, thanks, Laura. That was very interesting. Okay, so there are always exceptions to these rules, and that was an interesting exception. Um, you know, you should. Why I say a range of MPI processes, if the scaling is poor, i.e., if you run on twice as many processes and it doesn't go twice as fast, you need to find out what parallel routines for the bottleneck. Actually, this is much easier with a separate comms library. So if I asked you, now again, there are profiling tools which will give these results. I haven't covered profiling tools, but there are tools which will say your program ran for 2 hours and it spent 37 minutes in MPI or reduced, for example. But if you want to put manual timing in, if you have 100 calls to MPI or reduce, yeah, if you want to time how much time you spend in MPI or reduce, you're going to have to instrument 100 calls. If you funnel all your MPI or reduce calls through your own function, par_dsum, you only need to instrument one function. And so again, it's much easier with a separate comps library. However, often it's not the scaling that's poor. Maybe the performance is poor and you have to return the parallel issues later. But again, optimization is a huge subject in itself, but the important point is you need to know when your code stopped working efficiently, just like you need to know when your code stopped working correctly, so you only have to debug a finite amount of code changes. You need to know as soon as your code stops running efficiently, you need to know it. So you need to run regularly on a range of MPI processes, check the scalability regularly. So that's all I had to do on coding style. I'm now going to move on to issues with arrays, which are the bane of everyone's life. But are there any, so this is going to take a slight detour now. Are there any questions with that first? There's only about half a dozen more slides. And I know somebody wanted to know about this. Are there any questions about what I've said so far? Now, my last slides are going to concentrate exclusively on typical problems people have using arrays. Okay, so if there are no questions, so Fortran, it's actually quite interesting. I did a poll at the start, and it was a majority of Fortran programs. Fortran is you might nowadays call it a domain-specific language for scientific and technical programming. Arrays in Fortran are first-class objects. So I've said that if you have strided data to be sent and received, and that was one of my examples, don't send lots of small messages, you use MPI derived types. You don't need an explicit copy in, copy out. So you could do a copy in, copy out to a temporary buffer, but that's in a Fortran program. So why don't you just use Fortran array syntax? I can select an array subsection in using the language, but there are subtleties for non-blocking operations, which I will come. So now I've not done the animation correctly here, so I've given you the answer. What is wrong with this code? And I should have had an animation here. Okay. Allocate a buffer, call MPI ISend and deallocate it, okay? Hopefully it's obvious to you that that is clearly wrong, because I meant to hide these so I could ask you to give me the answer, but apologies for that. The non-blocking send may still be ongoing at deallocation. The code could crash or give unpredictable behavior, okay? So it's only safe to deallocate the memory after the matching wait. So this code, hopefully it's obvious to you that this code is wrong, okay? And this code will be equally wrong in C. If I did malloc buff, MPI ISN buff, free buff, that would be equally wrong in C, okay? But that's hopefully clearly wrong in Fortran, okay? Now, what you would like to do is this. If I have an real dimension MN array, okay, call it MPI ISN, and I want to send a slice of the second index. In Fortran, that is a non-contiguous array section. So I would have said use a derived data type. But a Fortran program would just say, look, in Fortran I can just do this, okay? This is one of the problems where the fact that MPI is implemented in a library is an issue, because the Fortran compiler assumes that when this code returns, everything is fit. Now, actually, what the compiler probably does with array syntax is, when you do array syntax, the compiler probably says, okay, David wants to pass a non-contiguous array subsection to this function. This function expects a contiguous array, okay? So what I will do is, under the hood, I will allocate a temporary buffer, do a copy in, call an MPI, call the routine, then do a copy back and deallocate. This is perfectly fine. This is transparent for any normal routine, okay? The problem is that the MPI ISN isn't a normal function. It is non-blocking. It carries on in the background, and the Fortran compiler by default doesn't know that. So buff may not exist when the message is sent. As issue is even more severe for non-blocking receive. For non-blocking receive, if you pass an array subsection for a non-blocking receive, you know, it will be deallocated and the receive probably won't have happened. So actually, although array syntax is very powerful, what it probably means, and it's perfectly legal for the compiler to do this, is a copy in, copy out to a compiler created invisible temporary. And that causes problems for non-blocking operations, which have long-lasting effects. So is it clear why? So array subsections to non-blocking operations is an issue in Fortran and should be avoided for this slightly subtle reason. Is that clear to the Fortran programs why that is? It is slightly subtle, and it's unfortunate because array syntax is an incredibly powerful feature of Fortran. So what do you do here? Well, note this is only an issue for non-blocking operations. If this was a blocking send, MPI send, that's fine, absolutely fine, no problem at all, okay? No problem whatsoever, okay? Or a blocking receive, MPI receive, no problem at all, okay? It's only with non-blocking operations is a problem. Other specific combine. So I am not a very modern. If you look at you need to look at the MPI manual, the MPI standard. There are ways in Fortran of labeling functions as being asynchronous. I think in modern Fortran. I think in modern Fortran you can label functions as being asynchronous, and so the compiler, you can tell the compiler I think it's called asynchronous. I don't know if any people are better, more Fortran expert than I am, but there are ways in Fortran of doing this and telling MPI, telling Fortran, look, this routine has long-standing effects, and then I think you later on tell it, look, it's over now, and you can deallocate it. So, but it's at the bounds of my knowledge of Fortran. So I would say avoid it. You know, do not pass non-blocking. Do not pass array subsections. You can do the subsection yourself. You can allocate the buffer. You know, you can do copy in, copy out yourself, and then you have control over when the buffer is deallocated. You can make it correct. I would still recommend using derived data types. It's not a big problem because for blocking operations, MPI send, MPI receive, it's fine, and often that's enough. It's often only a small. Often it's the halo-ing where this is the issue. If you look at the MPI standard, there are page upon page upon page describing all the subtleties, which I just avoid it because So I would say avoid array syntax even for contiguous arrays. So although this is probably okay, the Fortran compiler probably spots this as a, Fortran compilers are very clever. It will not do a copy in, copy out, but I would use the old-fashioned thing of just passing the pointer, the address, and so you should use derived data type, e.g. vectors for non-contiguous, where you would do this, one call type, for example. So yeah, it's nasty, but it's the point where the interface between Fortran and the library kind of breaks down. So I would just avoid passing non-blocking subsections, sorry, passing array subsections. Well, the compiler would have to know about MPI. Well, the compiler would have to know there was a problem with this MPI routine, and the problem with this MPI routine is that it has long. A compiler normally assumes that when a function returns, it has completed its operation. So, for example, it can free up any associated data. The problem with MPI non-blocking operations is they have long-standing side effects, and I think the way to tell so you need to tell the compiler this function has long-standing side effects on its operands. And I think the way you do that in Fortran is to say it's asynchronous. And if you use, I think this is included in the Fortran 2008 interface for MPI, that the interface will define these functions as being asynchronous, and so the compiler might do the right thing. It's all very hairy. So yes, the way that it should compile a correct code is to let the compiler know that this function has long-standing side effects, which I believe is asynchronous in MPI. Well, but it could, but why would the GNU compilers make a special exception for MPI? It's possible, yeah, it could, but it's only a problem here with Fortran. So I think, I mean, I can Google it. I think the issue is, but in OpenMP is built into the compiler. Yes. So yes, if we had enough money, we could pay the GCC people to make GCC compiler MPI aware, but I think they have better things to do. Sorry, more important. But yes, OpenMP. So I don't want to labor this point too much. I'm already over time. I've googled asynchronous Fortran subroutines. I think. So, the way to do it the correct way to do it in Fortran is for the function prototype to be labeled as asynchronous. Yeah, I think, or the arguments. And I believe, oh no, that's asynchronous IO. Or maybe, sorry, I need to look this up offline. It has been addressed in the Fortran 2008 interface, but you need to look at the manual to check exactly what the issue is. Is that okay? Sorry, I'm running a bit late, so I need to maybe get back on track. It's an interesting conversation, but maybe take it offline. So the equivalent issue in C programmers is arrays are not first-class objects in C programs. They're kind of hacked in after the fact. And okay, so I've shown you this diagram before. If you declare an array in C, a static array of size 4 by 4, it actually lays out a linear array of size 16, and the data is contiguous in memory, and it's nice. Okay, we just need to know which way it's contiguous. The problem is a lot of people in C do dynamic array allocation, and they'll do this. They'll see, okay, I want a 4 by 4 array, but I want it to be declared at runtime because I don't know it's going to be 4. It might be, and so I say I'll have this array of pointers. Okay, array of 4 pointers, which is so X is actually a float double star, which points to an array of 4 pointers, okay, which I've mallocked here, and then I malloc all the what you might want to call, if you're a C programmer, rows, okay. So this is a standard idiom in C, okay. The problem is there's two problems here. The data is non-contiguous because each of these array, what you might want to call as rows in C, or columns, depending on how you draw them, has been mallocked separately. And so we can't use vector data types to send non-contiguous sections because we don't know where the data is in memory. You also can't pass X to an MPI routine. You have to pass the address of exit, because you pass X, you want the data. So people, if you use dynamic array allocation in C and you do it in this manner, you have to be careful. The trick is you have to make sure that your array is malloced as a single object. So I have provided a routine called ralloc, which has two nice features. First of all, the data is allocated as a single malloc, and so you can use derived data types to pick out rows and columns because the data is allocated. Rather than you still have this horrible dummy array of pointers, but you basically fake them up. You make them point to the correct place. The way you do it is you allocate the array, the data as a single block, and you fake up these pointers to point to the correct place. So you still have a 2D array, which you can call xij, but the data is contiguous in memory. The nice thing about ralloc, you can do this by hand, but ralloc works for any number of dimensions, and it makes sure that all the data is contiguous, including the pointers. That means you can now free this with a single free. If you do this by hand, you tend to have to free it from the bottom up, but this means you can free. So ralloc is a very nice routine, which I got off a colleague many years ago. I've supplied it, and I have some examples. But people sometimes call these ragged arrays in C. This multiple mallocs of pointers to pointers is a real problem in MPI, because MPI expects linear buffers of data. Okay, so you wouldn't be able to broadcast this data as a single array because it would be 4 broadcasts. The trick is have a clever dynamic array allocation routine. Here it's called ralloc, that does things and gets all the data at runtime, but in a single malloc. And there's a bit of messing around there, and I have some examples which I can explain this afternoon if you're interested, but they're there in them. So conclusions, these conclusions haven't been very well updated, but run a variety of machines to debug, keep it simple, maintain a serial version, don't assume all parallel bugs are parallel bugs, and find a debugger you like, which is going to be an issue, but rather bland conclusions. But that talk took slightly longer than I expected, but it's good that we had some questions. That's the last talk. Are there any questions about that people have? We're slightly over time. Apologies for that. Okay, I'll fix this up later. I've done something stupid. But we will resume at, well, I'll back on the line in just under an hour to answer questions. Yes, the issue with malloc is only for 2D or higher arrays. So I know what somebody's going to say now. They're going to say what they do. I don't understand what's happened here. I've done something very stupid. Oh, no, there it is. Sorry. I just shared the wrong slide. Okay. They're going to say, you're going to say, oh, I'll do malloc of and then I'll do X of you're going to access your, then the people do this. So people C programmers love doing this. They linearize their, I mean, you can do that if you want, but that is assembly language programming. That's programming from the 1970s. It astonishes me that we're in the 21st century and the C compiler, well, sorry, that C still can't properly deal with multidimensional arrays. I know C++ fixes these issues and things, but you can do that if you want, but I think that is madness. And sorry, compiler should be your friend, the language should be your friend, and it's, if you're a 3-dimensional array, you should be able to say X, I, J, K. So yes, it is an issue with 2D arrays, and some people say, I'll make all my arrays 1D and do all my indexing by hand. Well, you can do that if you want, but you're giving yourself an awful headache. Very unreadable code. And I know you can stick it in a macro, but as I said, it is the 21st century. The compilers really ought to be able to help you with these. Yeah, I'm wittering a bit here, but you're right. It is an issue with 2D or higher arrays. So yes, if you were writing a code which dealt with arrays of particles, which were just numbered 1 to n, and not on a grid, then you're fine. You're fine. Again, it's only an issue for 2D dynamically allocated arrays. Statically allocated arrays are fine in C. So that's a case where you might want to just make the number of processes a compile time constant, so you can dynamically allocate your, in fact, not just the number of processes, but the decomposition, the number of processes px, py, pz if you had a 3D decomposition. Again, you might think that's inelegant, but it can make your life a lot easier. So I realize why I've done this wrong. This is I forget. I have I of course get the wrong time. So you know, I will be around, as I said. Especially as it's such nice weather, I don't know if people are going to stay around from there. But you know, as advertised, I reordered the lectures, but I will be around to answer questions in that slot. The one thing I would say is please fill in the feedback. I don't know if the feedback is open yet. I will check, but you will get reminder emails from my colleague Claire. You know, there's some subtlety of opening up the feedback, which means she may not be able to do it immediately. Yes, so let's just check. Yes, so I know I'm over time, but it is very important. I will show you where the feedback. Now you will get reminders about this, but so if you go to the main, I should really put a link on the course materials page, but on the main MPI page, your entry point here, today you'll have done the join session, but if you scroll down, Claire's already put up all the videos, which is very efficient. There is a feedback at the bottom. So because this course was part funded by the PRACE project, then we use a PRACE feedback form. It's very similar to our own, but on a different site. And you know, would very much appreciate your feedback. You know, what you thought about the course and comments, just to make it clear to people. You know, we do take this feedback seriously. It doesn't go into a black box, into a black hole. We do have regular training meetings once a week where we review the feedback from recent courses and act on it. The feedback is by default anonymous. I think, I don't know if there's an option to put your contact details in here. So there isn't a specific place now. By default, the feedback is anonymous, deliberately to allow you to express your opinions. Good feedback is great, makes us feel good about ourselves, and we can think how good we are. Poor feedback is equally important because we act on it where appropriate. If you had a specific question which was specific to you, then you're welcome to put your contact details in one of the boxes there if you wanted to. But by default, it's anonymous. Sometimes people have particular questions which require us to get to them, and in that case we can't get back to you unless we know your contact details. So you're welcome to put your contact details in there if it helps you or if you think it helps us, but by default it is completely anonymous, deliberately. Okay, so that really is the end of the course. I'm going to have a break for lunch now. I'll be back online at 2, here to answer your questions for the final session. But I hope you've enjoyed the course. I hope you find it useful, those of you who have accounts on NextGen.io, they will be open for a few weeks. I'll try and find out exactly how long, but it's all been done at the last minute. But you know, they are not going to be shut off. You should have access to them for the next week or so to carry on with the exercises. The course material will be available on the web page, a separate previous courses web page for as long as the Archer 2 service lasts at least. And the videos will be there and the slides. And I'll upload. I made changes to that presentation. I'll upload those as soon as I get a chance. So again, goodbye everyone, and maybe hope you enjoyed it.